Next, let's see how to add the children we just found to the spanning tree. But first, we need to filter out any children that are already in the tree. Let's begin with properties that tell us whether a tree contains some value. Property 1. If E is equal to value, then the statement tree node ECS rest contains value is equal to true. Property 2 says that if E is not equal to the value, then the expression tree node ECS rest contains value is equal to the expression tree rest contains value. Property 3 says that the expression the empty tree contains value is equal to false. In other words, we cycle through the nodes in the tree until we find the value. Now let's remove the values that are already in the tree. First, we convert the remove expression to the not-in-tree function. Elements of VS that are not in tree T is equal to the output of not-in-tree function, where the input tree is T, the values are VS, and the new values are empty. The following properties describe the not-in-tree function. Property 1 says that if tree T does not contain the value, then the output of the not-in-tree function, where the input tree is T, values are the stack value, rest, and the new values are result, is equal to the output of the same function with the same tree, and the values are rest, and the new values are value, result. Notice that value has been moved from the value stack to the new value stack. Property 2 says that if the tree T does contain the value, then the output of the same function, where the values are value, rest, and the new values are result, is equal to the output of the function, where the values are rest, and the new values are result. Notice that value has been popped, but it did not get pushed to the new values. Property 3 says that the output of the function, when the values are empty, is simply equal to the result. Next, here's how to add the new values to the tree. The result of pushing values A rest to tree T is equal to the result of pushing values rest to the tree node A and T. Property 2 says that the result of pushing an empty value stack to tree T is just T. Notice that we constructed new nodes with the values and pushed them to the tree. Now let's use the functions above to add a node's children to the tree. If the length of stack T minus 1 minus back I is equal to I, and the element at index I of stack T is the node with value and CS, and elements of children that are not in tree T are new elements, and the result of storing node value new elements at index I of stack T is equal to updated tree, then the result of adding children to tree T as children of the node at backwards index back I is equal to the result of pushing values new elements to the tree updated tree. Notice that we update the parent node's children attribute, which is initially empty, with the new elements first. Then add the new elements to the updated tree. Let's try to prove that the result of adding the stack 2, 1 to tree with node 0 as children of the node at backwards index 0 is equal to the stack node 2, node 1, and node 0 with children 1, 2. We can show that the length of stack node 0 minus 1 minus 0 is equal to 0, and the element at index 0 of stack node 0 is equal to node 0. And the elements of stack 2, 1 that are not in the tree node 0 is equal to the stack 1, 2. And the result of storing node 0, 1, 2 at index 0 of stack node 0 is equal to the stack node 0 with children 1, 2. And we can prove that the result of pushing values 1, 2 to tree node 0 with children 1, 2 is equal to the stack node 2, node 1, and node 0 with children 1, 2. Finally, we can compute the spanning tree. First, convert the spanning tree operation to the spanning tree function call. Spanning tree of graph G starting at node V is equal to the output of the spanning tree function where the input graph is G, backwards index is 0, and the spanning tree is node V. Notice that the spanning tree initially has one root node with value V. Now we can recursively build the spanning tree as follows. If the children of the node at backwards index back I of tree T in graph G is equal to CS, and the result of adding CS to tree T as children of the node at backwards index back I is equal to the new tree, then the output of the spanning tree function, where the input graph is G, backwards index is back I, and the spanning tree is T, is equal to the output of the spanning tree function, where the input graph is still G, backwards index is now back I plus 1, and the spanning tree is the new tree. We use the above property to find the neighbors of the node at position back I of T and add them to T. Only the neighbors that aren't already in T are pushed to T. Then we move to the next node by adding 1 to back I, and repeat this process. The next node might be one of the neighbors we just pushed to the tree, or a node we pushed a while back. In order to start at the bottom of the spanning tree and move up, as we do in this algorithm, we index backwards. In contrast, if an algorithm requires us to start at the top of the stack and move down, we would index normally. Let's try to prove that the output of the spanning tree function, where the input graph is pair 0, 2, 2, 4, 2, 6, backwards index is 1, and the spanning tree is node 2 and node 0, is equal to the output of the same function, where the input graph is the same, backwards index is 1 plus 1, and the spanning tree is node 6, node 4, node 2, and node 0. We just have to show that the children of the node at backwards index 1 of tree node 2 and node 0 in graph 0, 2, 2, 4, 2, 6 is equal to the stack 6, 4, 0. And the result of adding stack 6, 4, 0 to tree node 2 and node 0 as children of the node at backwards index 1 is equal to the stack node 6, 4, 2, and 0. We're finished when the backwards index is equal to the size of the spanning tree. In other words, if I is equal to the length of stack T, then the output of the spanning tree function, where the input graph is G, backwards index is I, and the spanning tree is T, is equal to T. At this point, the backwards index is too large. For example, if the tree has 4 elements, the maximum forwards or backwards index is 3. We reach this state when all connected nodes have been processed.